Euler's formula seems very complicated and abstract, and actually it is. However, we can approach it with some really simple technique and actually prove it. And let's start by first introducing the idea of Maclaurin series. It is a method of approximation. It can approximate a function. It can convert a function into a combination of many polynomials. Because in many cases, there are many complex functions out there that we can't actually integrate them directly. We have to convert them into Maclaurin series or a Taylor series. In this case, let's first start by finding the Maclaurin series for the sine function. The first derivative of sine is going to be cosine at 0, which is 1. Negative sine at 0, which is the derivative of cosine, is going to be 0. And the next one is going to be negative cosine at 0, which is negative 1. By repeating this process, you can actually see that the derivatives of a sine function actually repeats in a pattern. 0 to 1 to 0 to negative 1 to 0 and starts repeating. And by knowing this pattern, we can actually write out its Maclaurin series, which is going to be x minus x cubed over 3 factorial plus x to the 5th power over 5 factorial minus x to the 7th power over 7 factorial. Goes on and on. There's a similar pattern with cosine derivatives, which is going to be 1. And cosine derivative, which is negative sine, is 0. And negative cosine at 0 is going to be negative 1. It repeats. And the next derivative is going to be negative sine at 0, which is 0. Goes on and on. So then we can write out the Maclaurin series for the cosine, which is 1 minus x squared over x factorial, 2 factorial, plus x to the 4th power over 4 factorial, goes on and on. Then it's something tricky. No, it's not actually tricky at all, because natural exponential function is one of those amazing functions that you can just take its derivatives so easily. At 0, it's going to be 1 all the time. However, things are a little bit different for the ix, e to the ix. It's going to be 1. It's going to be ix times 1. Then it's going to be ix square 1. This is its second derivative. And because it's 1, because e to the I times 0, which is e to the 0, is 1. It goes on and on. And the thing here is that imaginary number I squared is negative 1. So actually, then we can write out the Maclaurin series for e to the ix, which is 1 plus ix. And because here is I squared, which is minus, and plus. Nope, sorry, it's not plus. It's actually minus cube over 3 factorial over 2 factorial, and plus 4 x to the 4th power over 4 factorial. Here actually I to the 4th power, but I to the 4th power is just negative 1 times negative 1, which is 1. goes on and on. Okay, and here is what's amazing. If you add up both the Maclaurin series for sine function and cosine function, you would actually get e to the ix. They have exactly the same Maclaurin series. See, so basically, we proved it. It is and there are many other complex proofs out there that you can look into, but this is definitely one of the most simple one, and it's really useful. It actually enhances your understanding on the Maclaurin series for the Euler's formula. And in the next two videos, maybe several videos, I'm gonna introduce applications on this Euler's formula. It is a really amazing formula, useful formulas. It has many applications, amazing applications. And thank you guys for watching. Have a great day.